Thanks a lot for the invitation. So this will not be career advice, I think. This is scientific advice, but there's basically nothing technical. It's more about how to do research for the purpose of advancing MIP solving based on my experience. Yeah, so feel free to interrupt. I think I have way less than 30 minutes of talking. I mean, I should have time for questions, but I think I have a pretty good budget for questions, so feel free to interrupt. In particular, a lot of this is my experience, my opinions. If you have a different point of view, then do jump in. Or shut up, yes. So yeah, so this is not necessarily career advice, or this is not necessarily good advice. But the intention I had was, you know, maybe there's a chance that I can convince someone here that there's still hope in doing research and improving MIP solvers. We've got, you know, young people in the audience like Shantanu, for example. So, you know, it's not too late. Not all is lost, Shantanu. So I hope you all enjoy memes. I only put one in this presentation, and then if you know your memes, you know there's a second part to it, which is here. So I feel that MIP solvers are really not getting a lot of love, and I'm going to look into why. So the way that people work on MIP solvers historically is the following. You get an idea, right? So far, so good. And then, okay, you implement it. What else is there to do? Okay, you test it. And then, okay, do you have good results? So do you improve over the state of the art? Okay, so if yes, easy, you publish it. You just tell your story. You said, here it works. I think I know why. Trust me. Now, if it doesn't work, well, you've already put in all this time. You're going to, you know, improve what you've done, right? So then you could just revisit the idea. Maybe you've looked at the test results. Maybe you've seen, you know, you look at the instances individually. You look at the debug output, and you see, okay, I see what's happening in this instance, and this is also happening in these other instances. I get a better clue of what I should be doing. Or maybe you can see, oh, wow, this new, I don't know, maybe I've coded a new heuristic. This heuristic is spending way too much time, you know, in these particular places or something. So I'm going to just try to write more efficient code, right? And maybe that will just tilt the trade-off in my favor. It could also be, for example, you see the instances, the improvement you have is really not working on some instances, right? And maybe on some instances, it's doing well, but on average, you're losing. Okay, so now maybe you're smart enough to look at the instances that are not working and say, hey, I can tell ahead of time which one of you is not going to work. I'm going to, you know, maybe there's some particular features to these instances that you can infer from the model, for example. I don't know, size of the model, you know, whatever, right? And then you can upfront have like just a simple if at the beginning of your new heuristic, let's say, and say, hey, if this is one of those methods that I think don't work, just don't run the heuristic. And then basically the performance on those instances won't change from default, and maybe hopefully all the instances on which you were winning still win. And then maybe you get good results. So plenty of stuff you could be doing, which is great unless, you know, unless that takes all of your PhD. So now, oh wait, sorry, there's a bit more here. So as it is, the only thing is publish, okay. But if you have implemented any numerical algorithm, you know that you want a stopping criterion that's going to control how many iterations of this you're going to do before you just stopped, because it's just not working. So you need an extra stopping criterion. You want to know, after a while, you know, how many times are you going to be doing this until finally you say, this is not going to be working. I've spent a year of my life on this. I can't afford, you know, especially if you're doing a PhD, you know, I need some papers. Okay, so then right? If there is hope, you continue. But if there is not hope, what? There's nothing else, right? You have this code that does nothing. You have these tests that are negative. What are you going to do, right? So can you publish something? So there's some tricks. You could look at your data set and you could say, hey, those instances, some of them work well. I think that I know a data set, like a specific instances, that if I run my code on this specific data set instead of running it on MIPLib, then maybe it'll be positive results on this specific data set, or maybe a few data sets. And then you can write a paper. It's not going to be as good of a paper because it doesn't improve general MIP, but you can publish it and maybe somebody will find it useful. So, but then even if you publish it, the big caveat is you still don't know why it works, right? You have a claim it works, but if somebody asks why, well, you have some intuition and that's it. But yeah, we're in the business of creating knowledge. So if what you give the community is spaghetti code that's not commented and works some of the time and you don't know why, is this arguably knowledge? So, and now this is the what I've called historical process to work on MIP solvers. And then my impression is that fewer and fewer people are working on MIP solvers because this process is really unsustainable now. And so why is it unsustainable? So I contend that the good ideas have been taken. Basically, all the low-hanging fruits have been taken. Or, this is not I'm sure there's going to be more breakthrough in the future, but it's harder and harder to make a breakthrough. And so that's one reason. And then some evidence of that is if you look at, this is the report of the latest skip release. So every year at the moment, there's a skip release. And you can see there's a 1% runtime improvement from this version of skip compared to the previous one, right? 1%. And, they're the state-of-the-art solver. There's other competitive solvers, but at the moment, skip is probably the most competitive. Either way, they have a lot of people working on this, and not a lot of progress. And it's not that they're not good. So yeah, so ideas, I contend that it's harder and harder to have a good idea. And also one reason that it's harder and harder to have a good idea is that, so this is a map of skip, right, where every bubble is like a plugin, and you have families of plugins like heuristics and node selectors, variables, well, branching, and so on and so forth, cutting. And then, you have a good idea, maybe, but then maybe something else in this whole thing is doing exactly what you have in mind, maybe in a different way you're thinking, or maybe it's doing some of what you have in mind. And so it's sort of hard to know the things that already are in skip, which, and I've put this under the things that hurt the implementation, but actually it's also justifying why it's hard to have a good idea. But the things that hurt implementation is that now you want to add something to skip, for example. You don't want to just add something in Cplex because nobody's ever going to use your code if you use the Cplex API. So ideally you put this in skip so that hopefully it's useful for someone. And then you have to deal with the complexity of skip. So it's about 800,000 lines of code just for the MIP part, right? And then you have LP and whatnot. So you have to know what you're doing if you want to improve skip, right? Because maybe there's a part of skip that interacts sneakily with, some, like let's say you're working here. I don't actually know whether this is branching or not. Let's say this is branching, right? All of the different branching rules. And then maybe this is heuristics. This is the biggest one, it's likely. So, right? And then some heuristics is actually collecting information that's relevant to branching. There's like a hidden link here that, there's information being shared between heuristics and primal and branching, for example. And so if you're not aware of that, then maybe you're not writing the best branching rule you can, or vice versa. So there's plenty of stuff happening here. The complexity is just mind-boggling. And so if you want to implement something, that means, well, maybe you're going to have bugs pop up that you can't really explain because there's a lot of complexity. So even the implementation is getting harder. It might be easier to write the first version of your idea, but then debugging and making sure everything works, that's getting harder and harder. It's sort of hard nowadays to justify using the branching plugin of Cplex and say, hey, it works with the Cplex API. Trust me, it will work in general. Okay, so implementation has gotten harder. Now, what about testing? So here I use some examples of the skip mailing list. So people who ask for help. This is from more or less 6 days ago. You probably know the person, actually. Student in ISYE. But anyway, it doesn't matter who it is, right? It's a person who writes to the skip team and asks for advice. And so what is it that they encountered in their tests? So here, they use a 48-core virtual machine, right? So anyone who knows anything about MIP testing probably has alarm bells ringing. And so, but she detected correctly that this was a cause for problems, right? So she's done some experiments on single core, so exclusive, and then experiments on all cores, so all jobs, all cores, right? And then she says, oh, the solving time can go up by up to 70%, right? So if you're trying to determine whether your new idea improves the MIP solver and you have variability 70%, right? And maybe your improvement is going to be 1%, how do you even test whether you're right or not? So then the right thing, ideally, you can afford to run everything in exclusive, only one core. But problem is when your department buys compute, they give you 48 core machines, GPUs, and sometimes it's virtual. You have no control over what's going on. How do you make that work? So that's how it is in my department. So we spend a lot of time complaining about that. So that's an issue, right? You want maybe to detect an improvement of 1%, and then you have to deal with all of this that's basically noise in your results. Another thing is, this is a bit older, but also the skip mailing list. Right, this person says, hey, the performance is affected by the order of the variables or the constraints. So they wrote to the skip mailing list asking what's wrong with skip. Okay. And then, so, some emails later, okay, I see seemingly minor changes in my model may produce surprisingly and unpredictable results. So they realize this is not a skip thing. It's a MIP solver thing, right? This is what we call performance variability. In other areas of science, maybe you say it's sensitivity to input, right? And so it's essentially the butterfly effect, right? That originally, somebody wrote a weather predicting software and they realized, oh, if I change like 1% of 1% of this digit of like this number in input, all the results change, right? So, and because MIP solvers are so complex, you have this performance variability issue. And I'm going to give you an example of how it can happen. So let's say, so here we're talking modifying the order of the variables and the constraints. So that means you have a MIP, maybe it's in LP format. So you have just a file, you swap some rows, and then you put this in your favorite solver, skip in this case, but other solvers that would still be true. And then the runtime changes. And so how could it happen? So solvers are hyper-tuned. They're going to have heuristics to determine when one particular plugin should run or not. And so let's say, okay, the solver starts reading this instance, and then it's going to do some pre-solving. So maybe it's going to tighten some bounds, for example. And then it has a budget to do that. And it's also going to check, am I successful in tightening the bounds? And maybe if you commute the orders of the constraints, it's not going to do the exact same tightening of the bounds in one particular run compared to another particular run where you've permuted the input. And so now maybe this doesn't have a dramatic effect, but then let's say you now start branching. Maybe you're going to branch on a variable that has its bounds tightened in one instance, and then in the other case where maybe the bound tightening didn't happen exactly the same, you're going to branch on a different variable. And now when you start branching on different variables, you can have dramatic differences in tree sizes and in runtimes. So this performance variability, which is very, very nice, Andrea has a paper on this, he just arrived, so he knows all about this. You can bother him if you have more questions after the talk.
I just came for that.
Exactly. I'm going to stop mentioning performance variability. You can rush to the coffee break. So yeah, this is another thing that makes testing harder, right? So here this is permutation of variable and constraints, but imagine where the case where you write a pre-solver and your pre-solver tighten some bounds, and now that will affect everything that will happen after that in the solver. So if, let's say, you improve the runtime with your pre-solver, how do you know that it's not just noise because branching happens differently, right? So that's one other factor that contributes to making testing much harder. Okay, I'm just going to show again this diagram. So we've talked about how ideas are arguably harder to get. Implementing is harder, testing is harder. Now, I think at least, in terms of publishing, the community is overall very aware that it's harder and harder to get results. So if you have a positive result, usually you can publish it, thank God, right? But if I talk to somebody outside of my community and I say, hey, we've got a 1% improvement, nobody's going to be impressed. But luckily in our community, people are aware, so this is not too bad. Now, you might say, well, this is academic MIP solving. Commercial solvers, they do just fine. This is the latest Gurobi version. And so in 1 year, they got a 13% speed up for MIP. Okay, so then you might say, well, clearly, these guys know what they're doing. They have good ideas and so on. Well, yes, but there's a team of, 20 people that are developing Gurobi. Not all of them work specifically on MIP, but they're working full-time on this, and they have decades of experience, and that 13% is not one idea, it's probably 13 or more sub 1% improvements, right? And I mean, some of these 13% improvements come from these LP improvements as well. So, right, so yes, they have reasonable improvements, but I think it's just they work very hard, they're very good, and they throw a lot of resources at the problem. So, well, this is their own internal benchmark, right? So, I think we can trust that they report things reasonably well. I mean, otherwise they could say 2,000%, Okay, so now this is the part of the talk where I haven't had time to animate everything nicely. This is why this looks very scary, but I'm going to go through it one by one. So actually, let me rewind a little bit. I'm going to just go back here. Yes, so what I want to talk about now is what I think is a good way of doing improvements in MIP solvers if you're an academic. Because my experience is that what I've shown just before is not so fun, especially if you're a PhD student. It's, you better hope the ideas that you're working on are good. You better hope that you have some other people that can explain to you, how to run experiments and so on and so forth. Otherwise, it's just a grind. Okay, so again, apologies for the lack of animations. So this is what I suggest as a way of doing things, and this is still very much, about as messy in the slides as it is in my head. So I'm very happy to take all the feedback you have, but this is what I have for now, right? So, and I call this scientific method to improve MIP solver because really it relates quite closely to, I think, what people do, for example, when they work in physics. right? Similar to MIP solving, people who work in physics, they just don't try random things and hope it works, right? Maybe that worked a few hundred years ago, but now everything is so difficult, right? Getting results in physics is so difficult, that doesn't work, right? And then there's a nice analogy where I guess you have people in physics who have a lot of resources who have, let's say, lots of telescopes or a large collider, and then they can gather a lot of data. And basically they do MIP and machine learning, right? So they gather a lot of data, they try to figure out, oh, do I see a pattern? And then there's the people who do theoretical physics who are going to be working with hypotheses and trying to predict what you might observe, right? And this is a bit closer to that. So what I think works well is you start with some hypotheses. And again, so now I'm going to have to switch to this slide. What's a hypothesis in MIP solving? So this is an excerpt from a paper. An hypothesis could be, okay, the up and down gains in branching are known for each variable and are invariant, right? The problem is feasible. If the problem is feasible, the optimal value is known. That's an example of a hypothesis. Okay. And then once you have that, you can derive an abstract model. And this is going to be familiar to some people, because the novelty is not the technical part. Right? So an example of an abstract model is, for example, okay, I've tried to represent the problem of branching as a decision problem because we know tools to study decision problems. And I want to be able to do theory on MIP solving because just doing experiments is super tedious. I want to do theory. I want to build knowledge. So, that's maybe obvious to a lot of you who work on theoretical objects to begin with, but MIP solvers are not theoretical objects. So we need a step of abstraction if we want to prove anything theoretical, right? So there's this step of abstractions that's necessary. And for example, you might think, oh, but for example, cuts, we understand cuts very well. Okay, well, maybe we understand one cut very well or each cut very well, but then, when you have all of these different separators, and then when you try to figure out what's a good policy to generate all of these different cuts, how many cuts of each type should I generate at each round? What's the optimal strategy? What the impact is in the branch and bound tree? At which node do you generate your cuts? All of these questions, they're currently answered heuristically in the MIP solvers. But surely there's a good way of doing things that we could prove theoretically, right? But right now, at the moment, all of this is experimentally driven. So, so we could, once we have an abstract model, we can do theory. So, for example, with the previous abstract model, you can prove, okay, well, branching in this context is polynomial time solvable. And here's what the size of the tree looks like, right? As an example. Okay, so now let's say you do some theory, and then you get results. And because we're talking about theory, results could be positive results, negative results, whatever you manage to prove or disprove. Okay, and then if you have results, you could stop there and say, okay, well, this is interesting in and of itself. I can publish that, right? You don't even need to do theoretical experiments, right? You can just publish that. And then now let's say you don't have results, but you think, well, actually, one reason you don't have results could be this abstract model is good. It's quite faithful, but it's too complex for me to do anything theoretical with that. Okay, so one way you could deal with that is you go back to the drawing board, either draft some new hypotheses or change your abstract model and then continue. But you could also say, look, I'm just going to use this simplified version, the simplified image of my MIP solver to now do some simulations. All right? And so what simulations are is basically you write something that mimics the behavior of MIP solvers, and now you can run some simulations. And it's so much faster because maybe you don't need to solve an LP. You could just have a branch and bound tree where you pretend to solve an LP at every node, but you actually don't. So you can run many, many more experiments. And now again, do you get results or not? If yes, maybe you publish. If yes, maybe you say, well, this is good evidence that it should work in MIP, right? And now you implement something in your favorite MIP solver, and you have all of this work you've done before that tells you it's much more likely to work than if you just had an idea that you had not tested in any way before, either in simulations or in theory. So, all right, and then, well, I'm not going to do all the other arrows, but basically, in this ideal diagram of how to do MIP solving research, the only thing is publish, but maybe this is ideal, but I truly believe that if you do this, whenever you find that, okay, this is not working, and this is what's happening with my current research project, that's, okay, we don't have the improvement we think we have, but at least we know which hypothesis we have made is most wrong, right? So then we know what to change and we know how to iterate, right? But it's not so much the case with this diagram here. So actually, I've used all my time, more or less. So I hope this was sort of interesting. And I know this is not technical. Oh, I did not finish with a meme. I had an extra meme. Okay, never mind. I'll just put the original one. I hope this was somewhat interesting. And I hope I have plenty of questions and unhappy people so that we can get some discussion going on. Yeah, thank you.